Hello, everyone. This is Frank, reference librarian at the McAllen Public Library, and welcome to Tech News. So, today we're going to be talking about self-replicating cells that were created in a lab, and also about new organism. So first, let's talk about self-replicating cells. So, just before we go on, I wanted to say, as you can see, I'm fading into the matrix. Because we're talking about tech news, so it seems like the gods of the matrix do not want me to be talking about this. So sorry beforehand. But I'm gonna try to do as much as possible before they fade me away into the matrix. Um, so let me go ahead and share an article with you that I had been reading in preparation um, of this video, and I hope that you all can see it. So the breakthrough here was the creation of a cell that could divide. And no, they did not create a cell from scratch. What they did was they synthesized some DNA, and based on that, they inserted it back into the organism, and the organism reproduced, and it was a new organism with a new genetic code. So let's go ahead and start with this. Um, these were scientists from the J. Craig Venter Institute, JCVI, and they had started with this work in 2010, and they started with mycoplasma cells. They destroyed the DNA inside the cells and replaced it with DNA that was built in a computer and synthesized in the lab. Excuse me. So the first organism in the history of life on Earth with an entirely synthetic organism. It was called JCVI Scene 1.0, and JCVI, again, it comes from the name of the lab. And I think I misspoke before. It's the first organism in the history of life on Earth with an entirely synthetic genome, not organism. It's called JCVI Scene 1.0. And you might be asking yourself, why tinker with DNA? Why tinker with nature? Why play God? So the goal of this type of research is to understand what makes life tick. This is a fundamental question we always had. What is life? What makes things living alive? And this has been going on since ancient times. So now we're getting at the heart of the matter, or so we think, right? I mean, you never know. Maybe we're still very far from it. Maybe we're barely beginning. So yeah, the essentially is to understand the fundamental rules of life, of how life is built. And then there are more practical goals aside from this fundamental philosophical question. And some of these is that they could use these cells as small factories to build drugs or foods, fuels, and to also detect diseases. And they could also function as tiny computers. So scientists, to understand life and to reach this practical goal, scientists have been trying to strip a cell to its minimum genome. And JCVI Scene 3.0 was too simplistic. It could not divide. There was another JCVI synthetic organism that was later on made. And then there was JCVI Scene 3A. And the way this one worked was by adding 19 genes, including 7 needed for cell division. And this variant has fewer than 100 genes. And an important piece of information is that E. coli have about 4,000 genes and humans have about 30,000 genes. So JCVI scientists work by constructing various variant strains through synthetic addition and removal of genes. And then the effects of the genetic changes were observed in the lab. And then this was a collaboration with other labs. So the other lab involved was National Institute of Standards and Technology, the NIST. So JCVI and NIST collaborated on this. And also MIT, but more on that later. So what was the role of NIST? So the role of this lab was to observe these changes on their microscope. And this was very challenging for them because the cells are very small and delicate, and putting them under a microscope for observation could potentially kill them because any kind of tiny force could destroy them. And then the MIT Center for Bits and Atoms, that's the other lab. Scientists at this lab built a microfluidic chemostat to keep the cells well fed and calm while being examined under a light microscope. So let me show you a small video here in this article that demonstrates what the MIT Center for Bits and Atoms did. So here it is. I hope that you all can see it. So yeah, it's timeless video of the cells of the synthetic organism JCVI scene 3.3a, and it shows you how they're growing and dividing. So the issue with the previous 3.0 organism, the JCVI scene 3.0, was that it ended up dividing into filaments, and other organisms were not dividing fully, and there were some of them that had some morphological defects on them. But JCVI scene 3a, it managed to form more uniform shapes, like an actual microscopic organism. So to sum it up, the goal of this research is to understand how every gene works in order to develop a complete model of the workings of a cell, and again to reach its practical and more fundamental goals of understanding life, and also to help our environment and help to detect diseases, etc. So let's start with another article that I also read for in preparation of this. And this one, it's a little bit earlier than the other one, but it does share some interesting details on synthetic organisms. So the organism created in this kind of work is SYN61. SYN stands for synthetic. I think it might have been obvious for a lot of people. SYN61. That's how they call it. And it has the largest genome ever synthesized from scratch, again, as of the time of the work of this. And it has 4 million genetic letters. Let's see. So the way they constructed this genome was by arranging short segments and assembling these short segments into 500,000 letter lengths by using yeast cells, which contain unicellular machinery. And genome engineers replaced the E. coli genome piecewise, section by section. And then each 500,000 letter segment was tested in partially synthetic bacteria before the 8 segments were brought together in SYN61. The new genome was recoded to add artificial components in the organism. So just a little bit of background on DNA. DNA carries instructions on the building of proteins, which are the primary biomolecules of the body. So this make up your hair, muscle, etc. These are built from proteins. DNA is built from strings of nucleic acids and proteins from amino acids. So nature has a repertoire of 20 amino acids, and their properties dictate those of the proteins that they conform. And therefore, those proteins dictate the composition or the nature of the bodies that they make up. But nature, even though it relies on 20 amino acids, DNA can accommodate up to 64, and there's roughly 500 in nature. Some DNA words or codons accommodate the same amino acid. There are 6 different codons for serine, for example, which is wasteful according to some researchers. The researchers in this project removed the duplications in the natural code to make it more efficient. So they made more space for new codons, for new genetic letters under. So they look for all the instances of the duplications and remove them with synonyms to make them a little bit more different. So that's how they got SYN61, which grows 60% slower. There were 18,000 changes total, and the organism is still alive. And this is a new variant of E. coli, and it does not have the machinery to translate viral DNA, preventing viruses from replicating. So this could have medical applications for it. That's essentially what this article was about. It's just describing SYN61 and just how the genetic replacements worked. Now, I'm going to stop sharing the screen. Before I leave, I want to leave you guys with a book recommendation. This is a book we have in the collection that I recommend everyone to check out, and it's called Life 3.0 by Max Tegmark. Life 3.0 by Max Tegmark. So previously, I read a book by Max Tegmark called The Mathematical Universe, in which it talked about this theory, this grand unified theory, or how should I call it, this theory of everything, where everything in the universe is described, and not only described, but everything in the universe is mathematics. So as we know, physicists constantly use mathematics to understand the universe and describe its relationships. But here, Max Tegmark is taking things a little bit further, and he's saying not only is mathematics describing the universe, mathematics is the universe. And when you think about it, the idea kind of makes sense because you in mathematics is not only numbers; you also have geometrical shapes, and you use geometry to describe space, and there's different kinds of geometries. We don't need to get into that, but it's a really fascinating book. And then he wrote this Life 3.0 book, which focuses on artificial intelligence, but also how it's related to life. So it's very relevant to what we've been talking about in this program. And let me see if I can find a good review. There's a review from Elon Musk on the back of the book, and it says, "This is a compelling guide to the challenges and choices in our quest for a great future of life, intelligence, and consciousness on Earth and beyond." So here you have it, Life 3.0. We have it in our catalog, and if you want, I can give you the call number here in this video. It's going to be 006.301 tag. That's the call number. So feel free to come by and find it and ask for Life 3.0 by Max Tegmark. It's a really awesome book, really awesome author as well. If you can find the other book, I highly recommend it as well. So without much further ado, I'm going to go ahead and end this live stream. Again, thank you very much for tuning in to this program, and we're going to continue with more. Bye-bye.